Welcome to the DX Today podcast, where you get facts and no hype. We are diving into a topic that is quietly reshaping the balance sheets of every large company globally. The true hidden cost of generative AI.
It's so true. It's no longer about whether the technology works, it's about whether the financial architecture supporting it is actually sustainable.
Right. And we're seeing this genuine seismic shift in IT economics. It's driven entirely by the scarcity and, frankly, the extreme cost of specialized hardware.
It is. And the investment numbers we're seeing just confirm that shift is happening right now.
Our sources indicate that something like 92% of large enterprises are currently increasing their AI investment, pouring significant capital into pilot programs and research.
They are. But here's the critical disconnect, and it's a big one. A shocking 95% of those current pilot programs fail to deliver any measurable financial returns.
95%. That's a staggering failure rate.
It's the core of the problem. The projects succeed technically in the sandbox. The model writes great code or it summarizes complex documents perfectly, but they just collapse economically the moment you try to scale them to real production traffic.
So the barrier isn't technical anymore. It's not, can we build it?
No, the barrier to successful AI adoption is no longer technical feasibility, but financial viability, pure and simple.
And this necessitates a completely new approach to financial management in the cloud. We're moving beyond general cloud cost management into a very specialized domain. Our sources are calling it GPU FinOps, or sometimes AI FinOps.
That's right. Traditional cloud FinOps was built on managing a utility, basically. Abundant, cheap resources. GPU FinOps is built on managing scarcity. It's about maximizing the density of assets that can cost tens of thousands of dollars each.
Okay, so let's really unpack this for you, the listener. Our mission today is to dissect why this GPU-focused discipline is so fundamentally different from what we're used to. We'll analyze the technical features that inherently drive these costs up and then provide the strategic frameworks you need to prevent this unit economics collapse when you try to scale your AI.
We want you to walk away from this knowing how to turn what is a massive investment into measurable, sustained value.
Because if you're making significant investments in accelerated computing, understanding GPU FinOps is, well, it's the critical shortcut.
It really is. It dictates whether your pilot remains just an expensive experiment or if it becomes a central, profitable engine for your business.
Let's start right there with that fundamental divergence. Most people are comfortable with the old rules of the cloud. Traditional cloud FinOps, it managed abundant, fungible resources, CPU cores, general storage.
Right. If you needed more power, you could usually just spin up another instance, another M5 or something, and your costs would scale pretty predictably with user traffic.
So why do AI workloads just completely shatter those assumptions?
They shatter them because the underlying economic physics are flipped. It's a complete inversion from a utility model to a scarcity model. Traditional FinOps, it operated in an environment of commodity, elastic resources. The whole game was just about right-sizing what you consumed and maybe securing some long-term reserved instances for predictable baseloads.
But the AI and GPU model is defined by scarcity. We've all heard about the global GPU crunch.
Exactly. The extreme demand for high-end GPUs like the NVIDIA H100 has created this massive supply constraint. And that scarcity means companies are often forced into these multi-year, multi-million-dollar commitments just to secure access to capacity.
So you're committing to buy the capacity before you even know if you can use it all.
You commit to buying capacity regardless of whether you need to utilize it 24/7 immediately. That drastically increases the financial risk right out of the gate.
And related to that scarcity is this issue of non-fungibility. In the past, if a CPU workload needed optimization, I could shift it to a different processor, maybe from Intel to an AMD chip. Is that even possible with GPUs?
Not without a tremendous amount of effort. The AI software stack is coupled so tightly to the specialized hardware architecture. Most notably, you have the NVIDIA CDA programming model.
The software is built for the chip.
It is. So if your job is optimized for a specific GPU generation, let's say the H100, you can't just move it to an AMD MI300 or, God forbid, try to run it efficiently on a generic CPU cluster.
What'd that take?
That would require a significant, often prohibitive re-engineering effort. We're talking potentially months of developer time, which immediately undermines any potential cost savings you thought you were getting. This non-fungibility raises the stakes of your initial hardware decision immensely.
Okay, let's look at the actual consumption profile then. We know traditional apps have those cyclical traffic patterns, the diurnal patterns that drop overnight. How does AI consumption look And why does that cause so many problems for our existing cost tools?
The consumption profile is characterized by two very distinct and challenging patterns. First, you have training workloads. They are wildly bursty.
What do you mean by bursty?
I mean, they demand 100% of the provisioned compute capacity for weeks straight, often running these massive coordinated jobs. Then, when the model is trained, the cluster often goes completely idle.
That's inefficient, but I guess it's at least predictable. What about the other side? Inference serving the model.
Inference workloads introduce the biggest utilization challenge, and that's because they are extremely latency sensitive.
Okay, so for something like a real-time chatbot or a customer service bot, you need the response to be instant.
Instant. You need the time to first token, the TTFT, to be incredibly low. We're talking under 200 milliseconds, or the user experience just completely collapses.
And to guarantee that low latency, especially during peak traffic, I assume you have to over-provision the infrastructure.
You are forced to massively over-provision your GPUs. You have to be ready for that instantaneous peak load. And the unfortunate reality is that the hardware might sit idle of up to 80% of the day just waiting for that next peak traffic surge.
Yeah, and traditional cloud autoscalers can't handle that.
They're terrible at it. They're designed to gracefully scale CPU resources up and down over minutes. They can't manage this instantaneous burst requirement. They can't bridge that massive utilization gap. So you end up paying for vast amounts of reserved idle capacity just to maintain that responsiveness.
So the entire goal shifts.
Yeah.
It's not about minimizing waste on abundant resources anymore. It's about maximizing throughput and hitting specific latency targets on a very scarce, very expensive resource.
And that changes the entire unit of billing. We're moving from the familiar vCPU hour to the GPU hour, and critically, to the token.
The token. This is the new financial variable, and it's what makes pricing so unpredictable.
It's the source of non-deterministic pricing, which is, well, it's a budget director's nightmare. When you consume AI as a service through platforms like GPT-4 or Claude, you're billed per token, which is roughly 3/4 of a word.
But why is it non-deterministic? If I query a database, the cost of that query is fixed. I know what it's going to be.
Because you know your input tokens, but you have no reliable way to forecast your output tokens, or, crucially, the internal processing that's required. You might input a 50-token query, right?
Simple question.
A simple question. But the model gives you this verbose, multi-paragraph response that consumes 5,000 output tokens. That's 100x variance right there.
And you mentioned this idea of a chain of thought process. What is that?
Yes. So if the model has to engage in complex internal reasoning, say solving a multi-step logic problem, that entire chain of thought process, all the steps it takes internally to get to the answer, consumes thousands of tokens behind the scenes. And that's true even if the final answer is very short.
So unlike querying a database, which is a deterministic system, every single AI interaction is a potential financial variable.
It is. It turns budget forecasting from a predictable spreadsheet exercise into a probabilistic gamble.
That brings us to a really complex macroeconomic trend that our sources are highlighting. It seems totally contradictory. They're calling it LLMflation alongside the Jevons paradox. So costs are going down, but we're being told spending is going to skyrocket. How do you explain that tension?
It's a fascinating and frankly dangerous trend for anyone doing financial planning. LLMflation is the deflationary force. The cost of raw intelligence is just plummeting.
How much are we talking?
Due to fierce competition and rapid hardware improvements, the cost to process 1 million tokens on a baseline GPT 3.5 class model dropped by over 280-fold between 2022 and 2024.
A 280-fold drop. So if the unit price is falling that dramatically, why are FinOps teams losing sleep over the total bill?
Because of the Jevons paradox. This is a principle from economics that says, as the efficiency or price of a resource falls, consumption increases. It increases to such an extent that total spending often rises.
We've made AI tokens cheap, so now we're using them for everything.
For absolutely everything. And this paradox is manifesting primarily through the rise of more complex workflows.
More complex than just a simple chat.
Precisely. We are moving so rapidly from simple, one-turn chat interfaces to these complex agentic workflows. Think about the evolution. A simple chat interface required one user turn. Summarize this article. That's a relatively low token count.
Right. And now, what does an agentic workflow look like when a user gives a high-level goal?
You give the agent a complex goal, something like, plan the social media marketing campaign for our Q3 product launch. That single user intention can trigger dozens, maybe hundreds, of internal autonomous model calls.
What kind of calls?
The agent might research competitive campaigns on the web, draft copy for 5 different platforms, run a self-critique loop to revise the tone, generate supporting images, and then schedule everything out.
That's a massive self-driven token burn, all from one prompt.
It is. The agent operates in this closed loop, generating exponential tokens for research, deliberation, action, all triggered by a single user input. So while the price per token is dropping rapidly, that's LLM inflation, the tokens per task are skyrocketing.
Because we're asking the models to do exponentially more complex multi-step work.
Exactly. And that is the critical FinOps implication. If you forecast your budget just based on the assumption of a decreasing price per token, you will fundamentally underestimate your total operational spend.
So a robust GPU FinOps strategy has to model for that.
It has to. It must model budgets based on the increasing complexity of the tasks being demanded by the business. You have to anticipate that aggressive rebound effect of the Jevons paradox. You have to monitor the tokens consumed per outcome, not just the price of the token itself.
Okay, let's shift our focus now to the hardware itself, the specific choices that dictate these financial outcomes. The A100 was the industry workhorse for a while, but the H100 is the new standard. Now, if the H100 costs 3 to 4 times more to buy or rent than an A100, how can our sources claim it can reduce the total project cost by 25% for certain workloads?
It seems completely counterintuitive, right? But the cost reduction comes from just unprecedented efficiency. The H100 isn't just a faster chip. It's architecturally optimized for large language models. The key cost-saving features are really threefold.
Let's start with the specialized components. What's inside?
First, the H100 features the specialized transformer engine. This is a piece of hardware designed specifically to accelerate the massive matrix multiplications that are the computational core of all GPT models.
So it's a custom tool for a very specific job.
Exactly. Second, it fully supports FP8 precision, that's 8-bit floating point. The A100 primarily used FP16 or 16-bit. Using FP8, you can effectively double your throughput with negligible loss in model accuracy, especially when you combine it with modern quantization techniques.
So you get twice the work done in the same amount of time. That immediately cuts the compute time and therefore the cost.
Correct. But the third factor, and this is the one that often determines real-world performance, is memory bandwidth. The H100 provides significantly higher memory bandwidth, 3.35 terabytes per second versus 2.0 on the A100.
Why should you, the listener, care more about memory bandwidth than raw FLOPs? We are constantly hearing about the trillions of floating point operations these chips can perform.
This is where we need to slow down and really understand the underlying physics of how these large models work. For massive models, performance is often memory-bound, not compute-bound.
Okay, give us an analogy for that.
Think of it like this. You have the fastest chef in the world. That's your compute cores. But the kitchen is designed with these really narrow hallways. That's your memory bandwidth.
So the chef can cook incredibly fast, but the ingredients can't get to the counter fast enough for him to work.
Exactly. During inference, the massive model weights, those are the ingredients, they have to be constantly streamed from the GPU's high bandwidth memory, or HBM, to the compute cores. And this happens for every single token that is generated.
So if the bandwidth is slow, the cores are just waiting.
They're starved. They sit idle, waiting for the necessary data to arrive. So you, the user, are paying for this extremely powerful capacity that is fundamentally bottlenecked by I/O speed. The H100's superior bandwidth alleviates that I/O bottleneck. It allows it to serve tokens much faster, which reduces the time the resource is tied up and drastically improves your cost efficiency.
That makes the FinOps decision framework much clearer. So where does the H100 financially justify its enormous premium?
For training, the H100 is almost always the superior choice.
Yeah.
If it costs 3 times more but completes your massive training job 4 times faster because of its acceleration, you've realized a 25% cost saving. And, maybe more importantly, you've significantly reduced your time to market.
And what about for inference, for serving the model?
For inference, the choice is much more nuanced. The H100 justifies its premium for the extremely large models, say 70 billion parameters and above, especially those facing high, consistent traffic.
But what if I have a smaller, fine-tuned model for an internal app?
Then the H100 is probably overkill. For smaller models, maybe in that 7 to 13 billion parameter range, or for internal apps with low, unpredictable traffic, the older A100 or even specialized inference cards like the L40S, they can often yield a better cost per token. You have to avoid paying that H100 premium, only to have 80% of its massive compute power sitting idle because your workload just doesn't max it out.
Okay, so scaling these workloads introduces another cost, what our sources are calling the interconnect tax. Since most modern models are too big for a single GPU, they have to be sharded or split across multiple devices. This requires high-speed networking, which comes at a premium.
It does. We're talking about technologies like NVLink and InfiniBand, which allow the GPUs in a cluster to communicate at light speed. Hyperscalers charge a significant premium for instances equipped with this high-speed fabric, so you're paying for the interconnect in addition to the raw GPU hour.
So the intuitive cost-cutting move would be to bypass that premium, buy cheaper GPUs without those specialized interconnects. What's the hidden cost of that decision?
The hidden cost is degraded utilization and massive, massive time waste. If you use cheaper, slower connected GPUs for a distributed training job, the devices spend a significant portion of the build time just waiting. They're waiting for data updates from their peers before they can proceed to the next calculation step.
And that waiting time is what you'd call the GPU bubble.
Precisely. The GPU bubble is billing time during which zero useful mathematical operations are being done. You are paying for idle compute that's just waiting on slow network latency. This is why FinOps teams have to track a metric called MFU model FLOP's utilization.
What's that measure?
MFU is the percentage of the theoretical maximum performance, the FLOPs, that your model is actually achieving. If your MFU is 20%, you're paying 100% of the bill for only 20% of the potential work.
So the core calculation for the FinOps team shifts from what's the hourly rate to what is the total duration of the job.
Absolutely. The team has to determine if the savings from a lower hourly rate on a cheaper, slower instance are completely wiped out by the much longer duration of the training job. A $3 an hour job that takes 100 hours is still far more cost-effective than a $2 an hour job that takes 200 hours because of poor interconnects and low MFU. In high-end compute, speed often equals savings.
We've focused a lot on the digital costs. But for any organization considering ownership or even specialized leasing, the physical cost, power, and cooling can be massive and are often just ignored by financial models.
This is the operational expenditure, the OPEX component, that can fundamentally undermine your TCO analysis if it's not included. The H100 is a heat-generating monster. Its thermal design power, or TDP, can reach 700 watts.
And a standard rack for training clusters might have 8 of those.
Exactly. A standard rack of 8 H100s can easily consume over 10 kilowatts of power just for the compute. That necessitates specialized cooling solutions, sometimes even liquid cooling.
That significantly increases the complexity and the cost of your data center floor space.
And the financial impact is cumulative. Our sources show that over a typical 3-year hardware lifecycle, energy and cooling costs can amount to nearly 20% of the hardware's initial purchase price.
20%, that's a huge hidden cost.
It is. So FinOps models have to factor in the electricity cost and the cooling overhead, which is measured by a metric called PUE, power usage effectiveness.
Let's define PUE quickly for the listener. What is that?
PUE is the ratio of the total amount of energy used by a data center facility to the energy delivered specifically to the IT equipment. A perfect PUE is 1.0, meaning every single watt is used for compute. But in reality, PUE is often 1.5 to 2.0 because of the energy required for cooling, lighting, and power conversion losses.
So if you ignore that PUE multiplier in your TCO calculation,
you're fundamentally underestimating the true total cost of ownership by a massive percentage. When we talk TCO, we aren't just talking about the price of the chip. We're talking about the entire facility infrastructure required to keep that chip from melting.
Okay, so that scarcity of high-end GPUs has fractured the market into 2 distinct tiers. We have the traditional hyperscalers, AWS, Google, Azure, and then these newer specialized GPU clouds or neoclouds. How do the economics of these 2 tiers create opportunities for what's called GPU arbitrage?
The hyperscalers charge a significant premium. We're seeing AWS H100 rates around $3.90 to $4.50 per GPU hour. We've even seen Azure reach nearly $7 an hour for on-demand access.
And that premium, I assume, pays for convenience.
It pays for convenience, for deep integration with their broader ecosystem, your storage, your security, your identity management, and a unified billing experience. They offer a robust but expensive environment.
And then neoclouds.
The neoclouds companies like CoreWeave, Lambda, or RunPod, they've emerged to aggressively exploit this premium. They focus solely on accelerated computing, offering bare metal access or highly optimized containers, and they undercut the hyperscalers significantly.
How much of a discount are we talking?
They're often offering H100s in the $2.20 to $3 per GPU hour range. That's a 30 to 50% discount on the on-demand hyperscaler rate.
A 50% saving is hard to ignore, but what are the operational complexities that come with that discount?
The operational costs are substantial, and you have to calculate them into the TCO. The biggest hit is often data egress fees.
The cost of moving your data out.
Right. If your main data lake is on AWS S3, you're charged significant fees. Sometimes it's pennies per gigabyte, but that adds up to thousands of dollars for moving these massive training data sets out of your primary cloud and into the specialized neocloud.
So the cost of moving the data can actually erode the hourly savings you thought you're getting.
Absolutely. Plus, you now have the operational complexity of managing two separate vendor relationships. You have to duplicate security compliance vetting, your SOC2, your HIPAA, and you're running compute in a fragmented environment. Arbitrage only works if the hourly savings dramatically outweigh all the egress and operational overhead.
So how do the most sophisticated AI organizations perform this arbitrage without just sinking into operational debt?
They employ what's called strategic multi-cloud compute arbitrage. The strategy is to utilize the strengths of each environment. So your data lakes, your application front ends, your light applications, they stay within the primary hyperscaler for those mature ecosystem benefits.
And the heavy lifting.
But the heavy, bursty, short-lived workloads, your large training runs or batch inference jobs, those are executed on the specialized clouds where the cost per FLOP is the lowest.
This sounds like an impossible task for an engineer to manage manually, given the constant flux in market pricing and resource availability.
It would be. And that's where the software killer app comes into play. Tools like SkyPilot or Ray abstract the underlying cloud provider. An engineer defines the job based on resource requirements. They just say, I need to run this training session on 8 H100s.
And the software does the rest.
The software handles everything else. It automatically scans all your connected providers. It identifies the cheapest available capacity in real time. It handles the cluster spin-up, executes the job, transfers the final results, and tears down the cluster to prevent any idle billing.
Which means the organization becomes immune to vendor lock-in because the workload is now decoupled from the vendor.
Exactly. They are always capturing the lowest market rate at any given moment. It makes agility a core financial strategy. It essentially weaponizes the market volatility by allowing them to constantly hunt for the best deal, whether that's a temporary discount on a hyperscaler or sustained low rates on a neocloud.
For the past decade, the orthodoxy in IT has been OpEx over CapEx, renting over owning. But the economics of AI are really challenging that fundamental belief. For the first time, ownership is re-emerging as a fiscally responsible option. We need to walk through the build versus buy calculus, especially when we're talking about the forever cost of inference.
When you look at the immense ongoing cost of renting GPUs 247 for inference, the math just flips. Think about a large customer service bot. It has to run constantly. This is a predictable, non-stop usage pattern.
So let's break down the economics of a single H100. Our sources suggest a purchase price of about $30,000, and we established the lowest rental rate is around $3 per hour.
Right, so based on just those numbers, the simple break-even point is 10,000 hours of continuous usage. That's approximately 14 months. If you rent the GPU continuously for longer than 14 months, you've paid more in rent than it would have cost you to just buy it.
But ownership involves more than just the chip itself. That 14-month break-even point doesn't reflect the true TCO.
No, it doesn't. We have to factor in the other components. The cost of the server chassis and HGX board to connect multiple GPUs, that could be $10,000 or more. The initial installation and maintenance fees, and crucially, the power and cooling overhead we just discussed. That 20% PX component dictated by PUE.
And once you factor in all those true ownership costs,
the break-even point compared to on-demand cloud pricing typically extends to between 14 and 18 months.
So the entire decision is a financial bet on utilization.
It is entirely a bet on utilization. If you rent via the cloud that's OpEx, you pay only for what you use. If your workload is spiky and only runs 20% of the time, you pay 20% of the maximum cost. This is great for unpredictable R&D usage.
But if I buy CapEx, what's the danger?
The danger is underutilization. You pay 100% of the initial capital cost regardless of usage. So if you spend $500,000 on a cluster and you only run training jobs 20% of the time, your effective cost per hour just skyrockets. It makes the investment highly uneconomical. The money is locked in.
Therefore, the optimal strategy for most large enterprises ends up being a hybrid approach.
Absolutely. The hybrid model is essential. You buy the baseload capacity you need for predictable 24/7 operations, your core inference serving needs, and then you rent the burst capacity, the significant but intermittent spikes you need for model training or seasonal traffic loads, using the agility of the cloud market.
We've covered the market dynamics. Now let's focus on tactical engineering waste. The highest costs aren't always visible in the contract. They're hidden in poorly managed technical states. Let's start with what might be the most insidious source of waste, the zombie cluster crisis.
Oh, the zombie cluster. It's pervasive and it represents massive monetary leakage. It's defined as a workload that has reserved an expensive GPU but is currently performing no useful work. It is dead, but it is still billing the company $3, $4, even $7 an hour.
How does a process crash without gracefully releasing these valuable resources?
It's usually a container failure. A complex training job might crash because of an out-of-memory error or a software bug. The computational process stops, but the container often fails to exit cleanly. It leaves the GPU memory locked, which prevents the cluster scheduler from assigning that highly valuable resource to a new productive job. It just sits there, consuming billing hours while doing nothing.
And then there's the more human element, the idle developer tax. I think we've all been guilty of this at some point.
It's highly relatable. A data scientist spins up an expensive A100 instance, costing $4 or more per hour, to run a quick test or an interactive experiment in a notebook. They finish the experiment, but they get pulled into a meeting, or they just forget to issue the shutdown command before heading home for the weekend.
And that one instance, let's see, $4 an hour times 48 hours for a weekend, that's nearly $200 lost for literally zero value.
And now scale that across a large R&D team running dozens of forgotten instances over the course of a year. This single human error can easily burn hundreds of thousands of dollars annually. It's a massive, silent tax on innovation.
So we can't just rely on human discipline here. The mandatory FinOps control has to be governance enforced by automation.
Mandatory. You need aggressive, automated tools. We call them reapers. These are scripts, open source or commercial, that continuously monitor your cluster utilization. If a reserved GPU is detected with utilization below, say, 5% for more than 60 minutes, the process is automatically flagged and terminated.
That sounds like it would require a big cultural change.
It does. Engineers hate having their processes killed, but it prevents this massive silent waste. Tools like Kill GPU Zombie demonstrate the community's attempt to enforce this kind of discipline.
Okay, let's move to a more subtle source of waste that ties back to the physics of the hardware. The bin packing and fragmentation problem.
This is a classic efficiency problem, but it's now applied to an extremely expensive resource. A physical GPU has a fixed memory capacity, let's say 80 gigabytes of VRAM. If your model requires 45 GB to load its weights, the operating system has to claim the entire 80 GB resource to guarantee contiguous space.
Which leaves 35 GB as stranded capacity, paid for but completely unusable.
Exactly, that's the bin packing problem. And fragmentation makes that stranded capacity unusable, even in aggregate.
How so?
Imagine your cluster has 10 GPUs, and across all 10, you have 100 gigabyte of available but stranded memory. Maybe 10 gigabyte here, 20 gigabyte there. If a new job comes in that needs 40 gigabyte, the cluster scheduler can't run it because the memory isn't contiguous in a single block. The scheduler is forced to spin up an entirely new, fully built node, which increases your cost despite having sufficient aggregate capacity already available.
So the financial solution isn't to buy more GPUs, it's to get smarter about how we slice and share the existing hardware.
Exactly. The key technologies here are NVIDIA MIG, multi-instance GPU, and time slicing. MIG allows a physical A100 to be hardware partitioned into up to 7 fully isolated virtual instances. This lets you right-size the slices to the workload.
So instead of giving a small 10 GB inference model the full 80 GB, you give it only the 10 GB it actually needs.
Yes. And you can increase the density of workloads per GPU by 2 to 7 times, which directly translates into dividing the hardware cost by that same factor. There are tools like Cast AI that specialize in using sophisticated algorithms to automate this bin packing and time slicing. They actively reconfigure clusters on the fly to fit odd-sized workloads onto the minimum number of nodes possible.
And that can have a huge impact.
This automated management can often reduce that stranded capacity waste by 50 to 70%.
Finally, in distributed computing, we have the inefficiency caused by gang scheduling. When a trading job needs to start, it requires all the requested resources, say 16 GPUs, to be ready at the exact same time.
And that necessity of synchronization creates what's called the hold and wait inefficiency. If a standard cluster scheduler sees that 12 of the required 16 GPUs are available, it often reserves those 12 and then just waits indefinitely for the remaining 4 to free up.
And during that whole waiting time, the 12 reserved GPUs are idle, but they are still billing.
Which means the organization is paying for expensive compute capacity that's performing zero useful work. It degrades your effective cluster utilization far below 50%. This is just another form of that GPU bubble we talked about, but this time it's driven by scheduling logic, not network latency.
This sounds like a problem that specialized schedulers were designed to solve.
They were. Advanced Kubernetes schedulers like Volcano or Kui are mandatory for large-scale training. They solve this by only locking the resources when the full quota is met, ensuring the job starts immediately when all 16 GPUs are secured. They prevent that premature reservation and the expensive idling that results from it. They guarantee that when the billing starts, useful work is immediately being executed at a high MFU.
We've established that software efficiency dictates financial outcomes. What are the 3 or 4 most powerful technical levers that engineers have found to instantly cut the GPU bill?
The transformation really comes from optimizing the model itself and how it interacts with the hardware. I'd say the biggest levers are quantization, FlashAttention, and speculative decoding, combined with a disciplined approach to spot instance orchestration.
Okay, let's start with quantization, which some have called the 4-bit revolution.
Quantization is a fantastic algorithmic cost lever. It involves reducing the numerical precision used to represent the model's parameters, its weights, from the standard 16-bit floating point down to 8-bit or even 4-bit.
And what's the physical, tangible saving that translates into a cost reduction?
It dramatically shrinks the model's memory footprint. An FP16 parameter requires 2 bytes of VRAM. An INT4 parameter requires only half a byte. This means the model becomes 4 times smaller in memory.
That has a massive impact on hardware requirements and therefore billing. Can you give us a concrete example?
Sure. Take a large 70 billion parameter model. In the standard FP16 format, it requires roughly 140 gigabits of VRAM. That forces you to use 2 80 gigabit A100 GPUs, potentially costing $8 or more per hour. If you successfully quantize that model to INT4, it only needs about 35 GB.
So it now fits comfortably on a single A100. You instantly have the deployment cost.
Yeah.
Or you could even run it on a much cheaper, less powerful inference card.
Correct. You get an instant 50% cost reduction for that deployment. Now, the natural question you should ask is, if the model is 4 times smaller, are we sure the accuracy loss is negligible? What are the trade-offs?
That's exactly the right question. Is this truly a free lunch, or does it only work for simple tasks?
For a while, the accuracy loss was significant, which made it risky for high-stakes tasks. However, recent research in advanced quantization techniques like AWQ and GPTQ has dramatically minimized that loss. For most common enterprise tasks, summarization, classification, code generation, the loss of accuracy is negligible. Now, there are edge cases, particularly in scientific or highly domain-specific tasks where you might need the higher precision. But for 90% of business applications, quantization is now a highly effective and low-risk FinOps lever.
Next, let's discuss FlashAttention, which addresses that I/O bottleneck we defined earlier. Why is this specific algorithm credited with saving companies millions?
FlashAttention fundamentally changed how the attention mechanism works. As we discussed, the massive bottleneck in the transformer architecture was I/O traffic. The standard attention mechanism was constantly reading and writing these large matrices to the slow, high-bandwidth memory, the HBM, outside the main compute cores. The GPU was spending all its time just ferrying data back and forth.
So the algorithm attacks the logistics of data movement, not the calculation speed itself.
Precisely. FlashAttention reorders the computation. It processes attention blocks in a sequence that allows the data to be kept almost entirely within the GPU's SRAM, that's the extremely fast, on-chip cache. By minimizing those slow, expensive trips to the HBM, it frees up the GPU to just do math faster.
And what is the financial return on implementing this? It's a free, open-source software library, right?
It is, and FlashAttention 2 offers a verified 2 to 3 times speedup in both model training and inference. So if an enterprise is facing a $10 million training budget, implementing this library can potentially cut the compute time and the bill in half. It saves millions. It's the clearest example of how pure algorithmic efficiency is now the primary determinant of financial outcomes.
Moving on to infant speed, let's look at speculative decoding and how it breaks the inherent latency barrier of serial token generation.
Standard inference is serial. The model generates token 1, then token 2, then token 3. This requires the large, expensive model to fully engage for every single step. Speculative decoding introduces parallelism by leveraging two models instead of one.
And one of those models is cheaper and faster.
Exactly. It uses a small, fast, cheap draft model to instantly guess the next 3 or 4 tokens in the sequence. Then, the massive, expensive target model doesn't generate the tokens from scratch. It just verifies those guesses in a single parallel pass.
So the big expensive brain is used for validation, which is a faster process than generation.
Exactly. The large model can verify 4 tokens in roughly the time it takes to generate 1 token serially. This drastically increases the effective speed and throughput. You can achieve up to a 50% latency reduction. And critically, it increases the throughput per dollar of your existing expensive H100 or A100 hardware.
Finally, for R&D training costs, the most effective lever is utilizing spot instance orchestration. You can save 60 to 90% on compute by using spare cloud capacity, but the risk is preemption. The provider can kill your job with very little warning.
And that risk of preemption means you lose both the monetary cost of the hours you've already run and the time you've lost. The financial solution is aggressive, robust checkpointing. This means saving the model state to disk every 5 or 10 minutes. If a preemption occurs, the orchestration software can immediately detect the failure and restart the job on a new, available spot node with minimal loss of progress, maybe 10 minutes maximum.
So the savings are worth the management overhead, provided you have that robust checkpointing mechanism in place.
Absolutely. Mastering spot orchestration with robust checkpointing is the single most effective lever for reducing the massive training costs associated with deep R&D. While there's future research into check-free training that aims to eliminate the I/O burden of constant saving, today, checkpointing is mandatory for any economical experimentation.
Inference is the forever cost, the expense that continues to accrue long after that training budget is spent. The fundamental economic tension here is between speed or latency and volume or throughput.
This is the decision that directly impacts your unit cost. To maximize throughput or volume, engineers use batching. They process 50 or 100 user requests simultaneously. The GPU loads the model weights once and serves all the requests in that batch, which maximizes your model FLOP's utilization and achieves the lowest possible cost per token.
But if I'm running a real-time chatbot, I can't wait for 100 requests to accumulate. I need a response now.
To minimize latency, to get that sub-200 meters response requests have to be processed instantly. That means your batch size is often 1. This just destroys efficiency because the GPU has to reload those massive model weights from HBM for every single user request. This action causes the cost per token to spike by orders of magnitude compared to a high-throughput batch job.
So engineers, who are naturally optimizing for speed, often default to the most expensive setting. The FinOps intervention must be to enforce financial discipline.
The FinOps team has to enforce the slowest acceptable standard for the specific use case. If the application is internal email summarization, which can easily tolerate a 2-second delay, that use case is 10 times cheaper than a customer-facing voice conversation that needs a 200 meters response. Using the fastest possible setting for a slow tolerance task is just reckless financial waste.
This focus on efficiency demands that organizations move beyond simply tracking raw cloud spend. The ultimate business metric has to be cost per task.
Cost per task is the metric that determines if a GenAI project is actually delivering ROI. We need to remember that input tokens are generally cheaper than output tokens, but it's the intelligence of the model that dictates the total number of tokens required to complete the task.
Let's revisit the example of the two models to illustrate this counterintuitive principle.
Imagine Model A costs a penny per 1,000 tokens. It's cheap and small, but it's less intelligent. It requires 5 turns of prompting research, revision, final generation to successfully solve the user's goal. Your total cost per task is 5 cents. Now, Model B costs 3 cents per 1,000 tokens. It's 3 times more expensive on a raw token basis, but it's smarter and solves the exact same task perfectly in a single prompt.
In that case, Model B is financially superior.
Correct. Its cost per task is 3 cents. This proves the essential principle of GPU FinOps. Better, more expensive models can ultimately be cheaper if their superior intelligence reduces the necessary volume of tokens required to achieve the desired business outcome. This is why that 95% failure rate exists.
That failure rate is the tragedy of pilot purgatory. The project works in the sandbox, but the unit economics collapse the moment it scales.
It's the cool factor trap. Projects are funded because they demonstrate innovation, but they lack a clear, measurable link to ROI, like replacing specific support labor or increasing conversion rates. If the projected inference costs, tracked via cost per task, exceed the value generated, the GPU bill will inevitably kill the project, regardless of how technically impressive it is. Financial viability has to be designed into the system from the start.
So what are the traits of the organizations that have mastered this, the ROI leaders, the top 5%?
They share three common characteristics, beyond just having great engineering talent. First, they commit to full-stack optimization. They don't just consume external APIs, they actively leverage internal levers like quantization, caching, and fine-tuning open-source models to control their own supply chain.
Second, they commit significant capital.
Yes, they exhibit high investment density. They allocate over 10% of their total technology budget specifically to AI. This signals a cultural commitment to productionizing these tools, not just experimenting with them.
And third, they integrate finance and engineering rigorously.
They establish formal AI FinOps control towers. These are cross-functional teams. They have finance leaders, senior engineering architects, and product managers who meet weekly to rigorously review and enforce unit economics, cost per token, cost per task, rather than waiting for traditional quarterly cloud spend reports.
Let's look at two success stories that embody this discipline: DoorDash and Pinterest.
DoorDash, in building its Gen AI contact center, faced extremely demanding latency targets. They needed sub-2.5-second response times while managing massive transaction volume. Their solution wasn't simply throwing H100s at the problem. They focused ruthlessly on finding the most efficient model for the job, selecting Anthropic's Haiku model and aggressively optimizing the entire inference pipeline for throughput. This balanced approach allowed them to reduce agent transfers by 49% while meeting those strict speed requirements. It proves that efficiency is the foundation of scale.
They match the intelligence required to the cost threshold.
Pinterest is another key example. They achieved cost reductions of orders of magnitude by shifting from proprietary, heavy external models to fine-tuned internal open-source models. And crucially, they ran this on unified, highly optimized AI infrastructure that abstracted the underlying GPU complexity. This platform agility allowed their engineers to switch hardware backends, for example, moving from a costly A100 environment to a cheaper L40S environment without having to rewrite their application code, maintaining cost flexibility over time.
To achieve this level of optimization and governance, you need tooling that operates at the GPU level, not just the generalized cloud level. You can't optimize what you can't see, the measure it rule.
Observability is paramount. We need tools that see exactly how much GPU memory and compute each container is utilizing. Specialized tools like KubeCost, which now integrates with NVIDIA DCGM, provide that granular visibility. This is essential for accurate chargeback models, ensuring that individual teams are billed not for what they reserved, but for their actual granular utilization.
And tracking those specialized API costs is also vital, especially with the rise of AI as a service.
Absolutely. Tools like Vantage provide a unified total cost of AI view. It consolidates your traditional cloud infrastructure costs, the H100 rental, with the opaque costs of external AI API consumption from vendors like OpenAI and Anthropic. Finance needs that consolidated picture to avoid hidden costs.
Then we shift to automation, the optimize it rule. What tools actively manage the cluster to reduce waste?
Platforms like Cast AI and Ops move beyond reporting into active cluster management. Cast AI, for instance, specializes in that automated bin packing and time slicing we talked about. Instead of relying on manual intervention, it constantly monitors workloads and automatically reconfigures clusters in real time to ensure every workload fits onto the minimum number of nodes required.
So the software is dynamically fighting the bin packing and fragmentation problems we discussed earlier, ensuring those Goldilocks clusters exist moment to moment.
It creates that high utilization density automatically. This capability is the difference between a cluster running at 30% utilization versus one running at 70% utilization, which is just a massive financial multiplier.
The FinOps Foundation provides a clear cultural roadmap for implementing this new discipline, starting with the crawl, walk, run framework. Let's detail those phases, as organizational alignment is just as important as the technology.
Crawl is the visibility phase. This involves mandatory technical and financial hygiene. Every single GPU instance, every container, every reservation must have mandatory tagging, an owner tag, a project tag, and a cost center tag. You have to gain visibility into your total spend across all providers. Without tagging, you can't allocate costs, and without allocation, you can't enforce discipline.
Walk introduces accountability and some basic controls.
This involves implementing showback. That means actively showing engineers how much their running models cost without actually billing them for it yet. This immediately changes behavior and encourages efficiency. This phase also mandates identifying and automatically killing those costly zombie instances we discussed, and enforcing the use of cheaper spot instances for all non-critical development and testing environments.
And run is full optimization, automation, and financial enforcement.
This is where you implement full charge. Chargeback teams are financially accountable for their usage. You automate spot orchestration for production training runs that are tolerant of preemption. And most critically, you enforce budget circuit breakers. These are hard technical limits embedded in the orchestration layer that automatically stop a training run, an experiment, or even an agentic workflow if costs exceed a set, predetermined financial threshold. This brings true financial control right into the engineering workflow.
And this emphasis on circuit breakers brings us to the future financial risk, the agentic explosion.
Autonomous agents pose the greatest potential for catastrophic, instantaneous bill shock that we have ever seen in cloud computing. These agents operate in these recursive cost loops. They try to solve a problem, they encounter an error, they self-critique, they retry, and they continue burning tokens indefinitely until they either succeed or run into a hard stop.
So a stuck agent is the new financial equivalent of an infinite loop, but one that is directly connected to the company credit card.
The cost can escalate in minutes. This necessitates mandatory guardrails that go far beyond simple utilization monitoring. The necessity of those budget circuit breakers becomes absolute. They have to be implemented as hard limits on the number of steps or tokens an agent can consume per task to prevent these failures from turning into financial disasters that wipe out months of efficiency gains in a single afternoon.
The governance must be able to fail safely, which really means failing cheaply.
Precisely. The ability to monitor, restrict, and kill financially errant autonomous processes is the final frontier of GPU FinOps.
This deep dive has moved us from the physics of the silicon and memory bandwidth all the way up to organizational governance and the future of autonomous compute. The key takeaway, above all else, is that the financial management of GPUs is no longer an administrative back-office task.
It is now a core engineering discipline. It's fundamental to success. The era of growth at any cost in AI is definitively over. The physics of scarcity, the volatility of the market, and the non-deterministic cost of tokens have mandated that the era of efficiency as a feature has begun. Success is defined by bridging that Gen AI divide, making your technical solutions financially viable at scale.
The organizations that win are the ones that leverage quantization, that arbitrage the multi-cloud market dynamically, and that enforce ruthless unit economic discipline through their FinOps control towers.
We've seen that the best solution isn't always the largest model or the fastest hardware, but the system that is most economically optimized, the one that requires the fewest tokens to get the job done.
Which leads us to our final provocative thought for you to consider. If better, more expensive models can sometimes yield a lower cost per task, how should you architect your future Gen AI system? The most efficient Gen AI systems are those that use a cheaper, smaller model for 90% of tasks, and only call the massive, expensive model like GPT-4 or the H100 cluster as a kind of financial escape hatch for the truly complex edge cases.
Think about the implications of that. How would you architect a system where the decision of which model to call is treated not just as a technical choice, but as a real-time financial transaction that governs your budget? That is the essence of GPU FinOps.